what we recently wrote this book on history of turbulence, somehow I never really appreciated before I read all the chapters to what extent this contradiction and mutual misunderstanding between people who did statistical attempts and statistical theory of turbulence, like Kreitman on one hand, and people on the other hand, more from mechanical and applied mathematical side, like Safman or Batchelor. It was quarrel. It was clear mutual hostility in many cases, which was, I always found it very difficult to understand. And eventually, I think I started to understand. So on one hand, there were people who were applying the most advanced at that moment, I mean, 50s and 60s, the method of theoretical physics, and they were applying it directly to the equation which describes the fluid. The results was mostly completely unsatisfactory. On the other hand, were people who deeply understood fluids, I mean really, who were doing experiments, participating in experiments, early numerics, and people who spend their life getting different types of specific solutions of fluid mechanical equations. And they were absolutely sure that all these statistical methods are completely sterile. They didn't get any physics. On the other hand, those people weren't familiar with these methods that were applied over there. So when you read, and particularly when there are some private remarks, it's unbelievable to what extent they mutually were antagonistic. And then one asks, is it forever, or there is some way to bridge it and to use methods of theoretical physics directly applied to the Navier-Stokes equation on one hand, and on the other hand, so that it will use the physical intuition. Just to give an example, for example, Safman physical intuition told him that the spiral vortex going like this, like a spiral, must play an important role. And it's a very non-trivial, it's a particular solution of Navier-Stokes equation. It's very non-trivial. And then he took this vortex and imagined an ensemble of these vortexes placed somewhere, everywhere, so that they would give you Kolmogorov spectrum for the second moment if you average the velocity field over this random combination of vortices.
Safman or Lundgren?
There was Safman, Poole, and Lundgren. There were many things. Actually, Lundgren was the first who explicitly wrote it. But then they were kind of combining them into something. It's a very good example. It's a particular solution of Navier-Stokes equation. That's true. On the other hand, statistics which is done to it is sheer triviality, and it gives a wrong answer. First of all, the second moment is not Kolmogorov 5, whatever this. Okay? On the other hand, Kreitman, who took Navier-Stokes equation and applied to it a perturbative approach, namely a root equation with a per-equation function. It has part of it which has response function, root equation for response function, and cut and made a closure. The result was totally wrong. And also this exercise had no physics input. I mean, you can do it with the Ising model, you can do it with Navier-Stokes. Where is the understanding of what is the physics? And it's not that you need to think long how to do it correctly. You need to understand that, first of all, we are dealing with example for which different, it's a statistical system. We want to ask about some expectation value, some mean value, and different expectation value are given by different velocity or vorticity or whatever configurations. Different particular configuration give contribution into different moments. That's the whole meaning of strongly fluctuating system. You cannot say that you have one idea and this one idea, it is this picture and it completely describes everything. Well, you can for burgers. Burgers, you know, there are or even for burgers there are shocks and smooth parts between them, and they determine two different parts. And this is a simple example of diffractality, and kind of you understand it. But more complicated system, what we would expect, that for any expectation value, we need to write respective conditional average. This conditional average may be some of them really determined by some very peculiar configurations. Okay? And the method to do it, of course, exists, and it's just again a standard method of theoretical physics. It's a path integral. So you need to write any average as an integral over all passes, and then look for the extremum of probability. If this extremum happens to be sharp for some reason, then it is this trajectory, unique trajectory, which gives the sharp maximum of probability that would determine it. Okay? And that's something which is the method itself, more or less, 70s and 80s was a time where kind of everything was understood on a technical general level of applying this method just for any system. This Martin C.G.Ross formalism and then some kind of technical advances into it. So by the end of 80s it was more or less ready, and it was explosively applied in statistical physics, in condensed matter physics, and gave, I mean, most of the interesting results when you look in modern condensed matter, they were obtained by this method. And in a sense, as I said yesterday, there are two methods of reality. Well, there are three methods. One is exact integrability, and another is perturbation theory, and the third method is possible. And exact integrability, in our case, is always kind of variant of conformal invariant that was so obsessed with conformal invariance, but I don't believe, and I don't think that many people believe that turbulence in its full glory is in any way completely exactly solvable. And in inverse cascades, in some cases, it seems to be that some subset of things could be exactly calculable, but not general. So, what is this method? Let's just, and I'll try to illustrate you. First of all, I'll tell you solution of one particular problem, maybe first real solution with the simplest problem related to Navier-Stokes equation. And at the end, if I'll have time, I'll try to explain why it's so difficult. And it's really that, I mean, we have a bridge, but it's so difficult to make any step on it. So imagine we have, I'll just start from generally, we have any equation of the type that L is whatever function of U, which is U could be a vector field, and this is whatever function of U is derivative and it's in nonlinearity, whatever you want. Viscosity, nonlinearity, everything is here. And you assume that you have some kind of external force acting on it, and this is where statistics enters, and we need to have input, which is in a sense already a huge simplification of reality. Reality is not like this as a rule. In reality, statistics appears out of random initial data and set of instabilities, an exponential separation of trajectory in this infinite dimensional space. But we want to have a clear input of statistics, so we say we have a random force which acts. Okay? And we want to find something like, I don't know, let's say U in the power n, the moment of it, and this average mean with respect to statistics of this force. So how we do it? We say, okay, we need to, this is equal as an integral over all velocity realizations. Here U is a function of coordinate in space. Okay? And it's satisfied, and I kind of symbolically, this equation. That's it. That's kind of formal exercise. So, okay, I don't like delta function, I like exponents, because we want to do saddle point. For saddle point we need exponents. So we say, okay, let's introduce kind of another field over which we can integrate, so that the result of this integration would give us the delta function. So take as this kind of an integral over. So integrating over P would give us delta function of this equation, just a formal trick. Now we see that this is something which statistics is known. So this need to be averaged over the statistics of F, and we know how to do it if F is Gaussian. If F is Gaussian field, then the average of the exponent of the Gaussian field is exponent minus 1/2 of the pair correlation of this field.
U to power n went down the drain.
Yeah.
Yes,
Right.
and here is U to power n. And thank you, Christoph, for reminding me about the most important part of it. So now, because I want everything in the exponent, what is the area? So, because I want everything in the exponent, so let me put it here into the n logarithm u delta function of t, because I expect that my measurement happens at the time equal to 0. Okay, and it's also part of this. Delta function of r, and I measured the point 0 at time 0. So that's my exponent, and I assume that my f is a Gaussian force, so it's completely determined by its pair correlation function. And for simplicity, I assume that it's like in time, and it has some function of r. And this function, I assume that I will be considering, let's say, if I consider direct cascade, it's usually something which is large scale and have a as a correlation. Okay? So now, if I integrate this over the statistics of f, it's an exponent of f, what I will get out of it, I will get the following integral. du dp exponent I p, my equation, ut plus l, dr dt minus 1/2, chi of r minus r prime, p of r prime, that's this term, fp. When I average over Gaussian f, I would get quadratic term here, and my extra term n logarithm of u as delta functions.
Why ut minus l, ut plus l?
Ut, how I define it here, plus, so here is also plus. Okay? And now I have an integral, which is an exponent. What I need to do, I need to apply saddle point approximation. Now, why would saddle point approximation work? Just kind of, it must have sharp maximum, and sharp maximum happens only if you have some kind of a small parameter. Usually, in quantum mechanics or in diffusion or whatever, we have here a large factor. Well, everything is divided like 1 over h bar. And we say h bar goes to 0, this is a big exponent, and we can really take only sharp. Here, we have large parameter potentially, and we can say we consider very high moment, or we consider the tails of probability distribution, which physically means that we want to get a probability of very strong fluctuation, and very strong fluctuation are very rare. So there's kind of a hope that if n is large,
That can become important when you take into account the recent data about the huge, highly localized concentration of radioactivity in the city of Tokyo.
there's an example of a strong and nobody knows how rare fluctuation. Okay, so in a sense what you do now, you say, okay, let's apply saddle point approximation. It's not guaranteed to work because we don't have large factor in front of the whole exponent and only in one of the terms. Which means that everything from now on will be like this. We'll be doing something, and at the end, if we'll happen to finish this road, we can look back and look at this action and understand if it's really sharp. Because from now on, there are no guarantees that it works whatsoever. So we look for extremum of this action, which means that we need to vary it with respect to t and require it to be 0. So if I take this part which stands here and make a variation.
Richard, you can also integrate on p more, right? In principle, it is quadratic. You can get rid of p.
Yes, in p I can integrate. It's quadratic, but it's technically easy to integrate if this is delta function, which means you have a white noise as a function, which means you consider equilibrium. Then this integration really goes. And by the way, for example, even for burgers, you can get non-trivial results for white noise, which is white in space too. That would be kind of equilibrium, but it will be not exactly equilibrium from the point of velocity. It's KPZ problem in a sense. It's different. When you take this delta function of derivatives, it was a different variants of KPZ problem, and they are kind of interesting and non-trivial. But when this is some function which has a finite kernel, integration gives you an inverse of it, and kind of don't get much far. Okay, so when you vary it with respect to p, of course what you get the equation which is ut plus L of u equal to the integral of chi r minus r prime, p of r prime, dr prime, and when you vary it with respect to u, you will get minus pt plus dl u times p equal to, when you vary with respect to u, this last term, you will get n over u delta function of t and delta function of t. And this is u at time 0, time of measurement. So let's look at this problem. First of all, we turn statistical problem into dynamical one. So we need to find a trajectory. This is a particular solution. There are two fields. This P is a response field. What Kreitman did, if you wish, that he was writing an equation for UU correlation function and UP. And this was a green function. And this was a pair correlation. So P is response. It's a field which tells you response. The correlation of P with U, it's a response of U to the force F. And indeed, it tells you that you need to take a pumping correlation function, integrate it with this P. Now, what is this P? It tells you what is this P. At the last moment, when you integrate this delta function at time 0, it gives you a finite condition that P at time equal to 0 equal to delta function of R, with a coefficient which is n over u over 0. Aha! It tells you that this P is delta function, and it just concentrates your forcing, it takes your forcing at this given point. But then you need to trace it back in time, and I want to know what actually happens to it. Now, this equation, for example, if this would be Navier-Stokes equation, L would be u grad u minus nu Laplace u. Okay? When you vary it like this and apply it here, it would give you here minus nu Laplace p, which means that for pressure, viscosity acts backwards. It's negative viscosity forward in time and positive backward in time.
Response.
Right.
Response.
The pressure went down the drain.
There is no, well, pressure is part of L, this equation. But if you want Navier-Stokes, what you really do, you add P div V and you add Q div P, which would be two extra fields imposing the conditions that divergence of V is 0 and divergence of P is 0, if you want incompressible. But for now, everything is hidden inside this L. What I now wanted to illustrate is that in a sense one can look at this equation and say, okay, I have huge continuum problem of averaging over infinity of trajectories. Now I just have a system of linear, partial, but a system of dynamical equation. This is known function, whatever, Gaussian, and Lorentz, whatever you like. You just need to solve it. It has a finite condition for the field P, and it has initial condition for field U, which is a simple statement that at minus infinity at time U was 0, or actually okay. Now first problem is the condition on U in the past, condition on P at the end. And indeed, these two fields propagate in different directions. Velocity is a well-posed problem if you go forward in time, because viscosity kills fluctuation. Okay? Now, if you go backward in time, immediately viscosity gives you instability. With P, it's other way around, just because it's a variation here. So P is a well-defined problem as you go backward in time. And indeed, you take this delta function, and as you go backward in time, velocity starts to spread it. It's getting finite bits. And then, nonlinearity or whatever advection happens somehow changes this. First of all, it's very difficult to find a solution of just, this equation equal to 0. It's not easy to find it with a force. On the other hand, this force is something which is large scale. I mean, this is a function which is, if you're interested in this, there's a large scale. Even if you integrate it with a delta function, it will be some function psi as a function of coordinate. But you need to find this solution, and it's, in a sense, kind of a non-trivial technical problem. But you would say, why would not do this numerically? Because after all, but numerically nobody was able to devise any method, but it is still possible. Just nobody so far. There were not that many people who understand this kind of theoretical physics are also able to devise a really non-trivial numerical algorithm. Because the problem is that one condition on P is posed on one end and conditional u on another end. If you could pose them at one end, then you can numerically solve it step by step. Now, because one is here and one is there, you need kind of, a procedure which starts from p and some u, go backwards, and then find here u, correct u that you started from, some kind of iterative procedure.
It's a two-point boundary
Huh?
It's a two-point boundary problem. It is then usually better to have a variational formulation. Start from the variation.
Which we are back to. Yeah.
So, not this one.
Yeah, of course, you need, that's right. Because in a sense, every time we were able to turn this into an ordinary differential equation, then usually we are able to kind of find a respective. Okay, so that's more or less how it looks. And of
But if
course,
you have to do numerics, you can go back to your original stochastic PDE.
but then you need to do ensemble of numerics.
Yeah.
Then you need to, not to do one trajectory, you need to direct numerical simulation, get a huge statistics, and then calculate average over the statistics. Now here, you need to find one solution, just one. But somehow in the non-trivial.
It's also, okay, it's also
Okay.
satisfying.
That's more or less the setting, and that's why it's so technically difficult. And this kind of a simple, there could be different situations. This could be velocity derivative, or okay? And it's, but it exists. And of course, in the simplest case, where well, this, for example, is a Burger's equation. It was all done back in the 90s. And it's already non-trivial, even though for Burger's equation, we usually know what is this type of. If we are interested in any values which is related to velocity differences or velocity derivative is always a shock which must appear. But then it's non-trivial, for example, how in the shock this field P, it's always a delta function, you measure it at a point. How it actually spreads, it stays smaller than the shock width, or it spreads and then shock would be an error. So it was also not that trivial.
Just a quick question. Where's the equivalence of the closure problem in this presentation?
It's kind of an opposite. A closure problem is if I would take this and
I
start a
understand,
perturbative
I
expansion.
understand, but there must be some consideration of difficulty at some point.
No, he's already done saddle point. So that's why
Ah,
he's in
There
the
is a, sorry.
This is by the assumption you have a settle. Okay.
Yeah, but this is an
There's
assumption.
an
The
assumption.
saddle point is sharp and the fluctuation.
Yes.
The fluctuations are sharp and peak.
Yeah.
But
I
it's
have
may
a
not be
question.
true.
Yeah.
When you do the saddle load, you also need some second derivative, the width of the distribution.
That's where I come. So in a sense, I mean, what we really did twice, once not exactly correctly with passive scalar, and Christoph corrected us, and second time with Burger's, that you solve this equation, you plug them into action, you find that the action indeed high, and that's not the end of story. You need to take into account fluctuation. You say, okay, now let's assume that apart from this solution, that my solution is this U naught of R and T, which we call instanton trajectory. Which means instant, which means that it has a finite lifetime. It just appears out of nowhere and gives me what I want, plus some delta U, and then I need to treat this perturbatively and up to Gaussian integration over this to find correction to the action of fluctuations. And then I could be sure that everything is okay. And we did it only once, honestly, for the problem with the groups. But now,
Let me ask a question. I mean, sort of, here you can sort of get rid of n dependence by some rescaling, or
no, it will be non-trivial and dependence. In a sense, the answer, for example, for Burger's would be something like exponent m logarithm m, and there will be a factor for which we're actually fighting, because it gives you PDF, let's say A. It gives you PDF which is the exponent of u 1 over A, something like this. Okay. So, in a sense, I mean, this is
I want to
non-trivial.
solve this equation for large n
Yeah.
again.
Yeah, sure. And of course, this is for large n, which means that this is indeed what makes action. Now, I want to show you something which kind of, not that exactly took us 10 years, but we started it in 2000 and we ended in 2010, and which is a really first non-trivial solution for Navier-Stokes, and of course for the simplest case, and this is a direct cascade into D. Now, direct cascade into D is, in a sense, border case. It's marginal, because we have this kind of a simple mental picture, like direct cascades all have anomalous scaling, inverse cascade all have normal scaling, and some even have this conformal invariance. Now, when we think why it is so, it's usually the thinking is either simple, like in inverse cascade you have self-averaging. In a direct cascade we have kind of this Lagrangian picture, which is in our review, and which actually many people develop, is that inverse cascade is something which is self-accelerating, which when you translate it into Lagrangian language means that the particles separate explosively. Particles separate explosively, then this is a mechanism of anomalous scaling from the viewpoint of Lagrangian trajectories. If you want to consider n-point configuration, which would give you some nth moment, then it is not in any way, even if n over 2 points here and n over 2 points here, after a while they all separate and it is a real n-point geometry which works. Okay? And it's important that the velocity field in which it happens non-smooth, which another way to say that we have a kind of a Richardson diffusion, an explosive power-like separation. Here we know that in this direct cascade, just from the fact that it is a cascade of vorticity, so we need V grad omega omega to be constant. This is the flux of vorticity, like in point 1, and point 1, and point 1, and point 2. And when you just do power counting, it would suggest that V is proportional to R, which means that it's kind of velocity field is small. Of course, it's logarithmic, which tells you that this, without singularity you cannot have a cascade. There must be finite dissipation in the viscid limit, but power counting just gives you a smooth velocity. Delta V scales like R, distance between points, and then if you solve the equation delta R dot equal to delta V, which is proportional to R, you get exponential separation of trajectories. Okay? So in a sense, it's kind of a border case. We know that really it gets exponential with a Lyapunov exponent, which itself depends on scale, but it depends on scale in a logarithmic way, so it's accelerating but not accelerating fast enough. So it's kind of a it's a kind of a classical direct cascade without just classical Kragman cascade. So what we actually did, we asked what is the statistics of vorticity in this cascade. First of all, we know the third moment, but if we would like to find omega in the power n, and it happened to be that if we really, from here, one would expect that omega correlation function has a zero scaling. If V has a first power, then omega has a zeros, which means that it's logarithm. And after Kreitman, we kind of expect this logarithm to be in the power 1/3, so that the third moment would have a L over R, where this is a forcing scale, and this is a distance between points. Okay? So if we would calculate this, and it happened to be this logarithm in the power n over 3, that would tell you that it's a scale invariant statistic. And we know from Gvida, for example, from numerics in direct cascade, that there are things which aren't scale invariant. If you look at the zero vorticity line, which are so beautiful in inverse cascade, in the direct cascade they are multifractal. So we know that in the direct cascade there are things which aren't scale invariant. For example, lines. So now we ask, what is it about bulk field? Okay, now let's do the same thing, which means that we write if, and I'll be very schematic now, but because I want you just give an idea what it involves. So again, we'll be looking at some dp, d omega, exponent I, p, omega t plus v grad omega minus nu Laplace omega, and we integrate it over force, and it gives us some function pp. Now, v now need to be understood as expressed through omega through Biot-Savart rule. So it's kind of everything is in terms of omega. Now, we want this. Of course, it means that it's actually we take omega coarse grained over some scale r, and then we raise it into some power, and we express it, expect it to be logarithm of L over r in some power. Now, when you write the respective equations like here, which would be again equations like omega t plus v grad omega, it's just usual Navier-Stokes equation with this right-hand side of forcing. And you write respective equation for this. It has a finite condition here, which is a delta function of t. and it is my omega. So it will be n over omega times 0. Here are equation. I have a finite solution for p. I have a solution. I have a condition on omega, and it's axially symmetric. Because vorticity is axially symmetric quantity. So you say, okay, if it's axially symmetric equation, I can look for axially symmetric solution. We all know that in axially symmetric flow, vorticity does not change. In axially symmetric flow, the nonlinear term exactly turns into 0. That's what happens. The moment that you don't have this term, this is a trivial problem. It just tells you that vorticity is pumped by some Gaussian force and dissipated by viscosity, and we all know that if you pump it by Gaussian force and it would have a Gaussian statistics, this solution exists. It is such contribution. It doesn't have any logarithms or whatsoever. It doesn't. It's just a trivial. And by the way, of course, for long ago with Migdal and Lebedev and Polgar, we did this type of solution for Navier-Stokes. They do exist. It's kind of a local maximum. This functional space, there are some idiotical, very small local maximum. Somewhere else, there is a huge real maximum which corresponds to Reynolds dependent, in this case, logarithm Reynolds. So what one needs to do in this situation? Then you understand that these fluctuations actually must play a role at the very beginning. So really, we cannot, if we say that P and omega are sum over M over angular harmonics, let's say we write it in a Pm, and this would be omega M. Then we can take P naught and omega naught, zeros harmonics, and they give you this trivial stuff. But then the other harmonics are important. And what can we do? Then one back to full nonlinear problem. So what we really did, and this we did with Lebedev, finished last year, what we started 10 years ago, 11 years ago, that we say, okay, what we actually want to find? We want to find the probability of very large vorticity. That's what gives you the contribution in a moment with very large n. So this will be a huge vortex somehow appearing somewhere. And of course this huge vortex will be almost axially symmetric, because just by the fact that it is so huge, and everything else try to strain it, but we know that you cannot strain a vortex which is very strong. If vorticity is much stronger than the strain around, then it will be almost but not exactly. And so what we did, we wrote it as P naught plus other harmonics and omega naught plus other harmonics, and we treated this as perturbation. In a sense, but this now we need to integrate over these degrees of freedom in the Gaussian approximation, namely assuming that they are small, but we need to integrate it and only then try to find extremum of the action which will be the result of this integration. Okay? And that's how you do it. So you, in this action, which stands here, P, here, where it is. What I need to get here, it will be something like P naught times Vm grad omega minus M, terms like this. You see, it's a quadratic with respect to this. So you integrate it over dPm d omega M. It's Gaussian integral. And essentially, again, as you do Gaussian integral, as a result, everything will be expressed in terms of correlation function between omega m and omega minus m at point 0, at point r. Okay? So, what we now need to find, we need to find a clear correlation function of vorticity in a field of our vortex.
What is omega sub m?
It's a harmonic, it's just a
Okay.
coefficient of angular harmonics for which we integrate. Okay?
Sorry, can I ask you about scales? Now you say you have a huge vortex. Now that huge is smaller than your injection scale or bigger than your injection scale or what?
It's much smaller. I'm interested in the statistics in the inertial interval, in the direct cascade. So,
it is,
and eventually, this logarithm, this is my injection scale, this is my measurement scale, cross-grain scale, this will be assumed large. I would exploit largest of this parameter and largest of this parameter. There's two parameters. This would give me several points, and this would allow me to solve the several point equation because they are also very complicated. But before, I need to get a normalized action, which means because action naively taken on this axially symmetric vortex give me trivial evolution. Now it's clear that all this fluctuation of changing shape of vortex would something which would really stop my forcing, because here I just have forcing. Okay? So I need to do this Gaussian integration, which technically means that I need to find a pair correlation function of fluctuation on the background of this vortex. Yes. So in a sense, what I need to do technically is to write equation on this pair correlation function, which will look like this. ddt, it's always look like this, and viscous term. But this would be my vortex, which I don't know yet. And that's what makes, again, it's always when you do this type of problem, you need to guess the answer, and that's what here your physical intuition helps. For example, I believe that for 3D, this Lagrange vortex would pop up in trying to find the respective configuration. So, in a sense, you see, I need to find this pair correlation function for arbitrary vortex. But of course I cannot do it, it's a complicated equation. So I need to guess the form of it. Eventually, when I find it, I will get my normalized action, which would look like P omega t plus V grad omega, I mean usual Euler equation. I will get extra term, which of a very strange form. It will be omega naught xc, and there will be d over dt, t omega, logarithm of omega with respect, this is a derivative with respect to coordinates, and omega naught is my zeroth harmonic. So I will get effective action, which will be completely in terms of my zeroth harmonic, because I express this pair correlation function in terms of it. And this extra term, which comes out of renormalization, would give me the extra term into action, so that after I write instanton equation with this new action, it would give me here extra term instead of this, which would be a non-trivial evolution, and which physically describes how fluctuation really stop growth of vorticity, which quantum tries to do. Okay? And this is absolutely the simplest problem which one can pose about the derivative, this is the velocity derivative, about the velocity derivative in Navier-Stokes. There's nothing simpler than that. Everything else in inverse cascade, 3D direct cascade will be much more complicated. And just last 3 minutes I'll spend why it will be so much more complicated. But when I look at the respective equation now, in the case where I would have a real non-smooth velocity field, something like Kolmogorov type scaling, I would realize that this answer would be not a logarithm of, this is actually Reynolds number, but a Reynolds number itself in some power. It's what somebody called Merkin scaling, right? So the derivative would be Reynolds and some power zeta n's for psi n's. And then when you look at this equation, how they actually have a form, you realize that it is something which comes at a very distant path from some fluctuation which has a forcing scale, and this fluctuation must somehow go and contract into a viscous scale and give me an answer which is a parametrically large. Now, as I learned from Uriel many years ago, that smoothness could be from two ways. First of all, you have a finite time singularities. Clearly, you look at your field and it has singularities there, singularity up to viscous scale. Or that the statistics is such that the probability of approaching singularity decays too slowly, which means that you really can get a moment which goes to infinity with Reynolds number going to infinity, not because it's a singularity, but because a probability of coming to singularity is great. In this language, it technically means that either my value of my quantity at the last moment of evolution of this instanton is parametrically large, or my action, the integral of this is large. And I can show, well, not mathematically, I'm not a mathematician, but kind of in a physical way, that the second possibility is practically could be ruled out. This surprisingly brings me to the following. One need to get finite time singularity solution to get any, I mean, not even anomalous scaling, even Kolmogorov scaling. To get out of here, one need to get a finite time singularity of Euler equation, not of
I couldn't follow the last argument. What you said before, of course, I agree with. But why do you need a finite time singularity?
Let me explain. Because when I look at this, and I spent years looking at this equation and trying different substitution. But what you realize that it's actually a Navier-Stokes equation with the right-hand side which is smooth. It's large scale.
Sure.
Okay? So, and the answer that you want to get must be something which has a viscous scale in it. Like, it must be large with a image now.
Yeah.
Okay? Now, it seems as if you have an infinite time, because you start at minus infinity, but it's not. Because everything which goes from any large negative finite time to minus infinity, I can describe. Because it's something where I really start from small fluctuation, and it's trivial. And you cannot get anything over there which would be of viscous scale.
In the direct scale, we need just time of order 1 to go to the lower scales. Why do you say large time?
And I don't, no. I mean,
I'm confused.
I need to find my solution on all time from minus infinity to 0.
To 0.
It technically looks like an infinite time scale. Maybe I don't need a finite time singularity. Maybe I can grow the singularity in an infinite time. The answer is no. All this scale of big times is unimportant. It all starts when you are for the unity. Okay? And in this respect, and then, inverse cascade is different. Because in the inverse cascade, we don't have viscosity. In inverse cascade, in a sense, all this game is about having singularity from the very beginning. But then again, it's a tricky thing how to do, because you don't want to treat viscosity when you treat inverse cascade. So you need to have such smart pumping which already took care of the direct cascade inside. I don't know how to do it. I was never able to. It's doable, but I just don't know how to do it. But in direct cascade, I'm absolutely sure now that it's a finite time singularity solution of Euler equation which must be found, and it will be different for different things. For du dx it will be one, and for omega it will be
You
another.
can put quotes on your finite time series.
Yeah, well, no, of Euler. I mean, finite time singularity of Euler equation, not of Navier-Stokes, of Euler equation. It's not $1 million. It's much more important than mathematical existence. Okay, so that's probably where I'm supposed to stop.
Thank you very much.
Something very minor. So in the business, you actually have to guess which kind of similar structure will contribute to the large n moments.
Yes. And it will be different for different geometrical configurations. For example, when we did it for, let's say, passive scalars, it depends what kind of you ask. You can ask for different derivatives, or hear about different types of derivatives, it will be different.
Now let us say we want to kind of have some insight on that guess from numerical simulations.
Would be nice.
Let's say, but say
Yes.
what kind of quantities we would look at when
From direct numerics, what I would expect. Somebody would tell me, the configurations that give the main contribution into vorticity, in the vorticity tails are configuration like this. Let's see. In 3D, if I sort out everything else and just ask what are local configuration, but I don't need only snapshot. I want a history.
yes, so
the local realization in space-time look like this, and this gives the main contribution info. That would give me an insight where to look for.
So let's say I look at Gaussian simulation and I throw away a lot of stuff except some very singular vorticity patches. And with this I see if I can reproduce the table. And will that...
Yes, in a sense, yes. You can say that, because when you do numerical simulation, you have all the ensembles. So you say, here is my tail, and where it comes from. What are those events that it comes from? From this and this and this region. Now I want to see also the last period of evolution before this, because that's important. I need special temporal dependence. Because without guessing the right answer, there is no way to proceed here. You see, I need to know the answer before I start getting it.
So that's in order to keep the smallness of the perturbation, right? Because otherwise, if you don't have the right solution around the term, the perturbation is going to be arbitrary.
In a sense, yes.
Right,
In a
that's
sense, yes.
clear.
And it's always a non-trivial normalization issue. So, in a sense, this is something which you really need a physical intuition. But then you write equation. In a sense that it's not just your hand wave.
Any further questions? Remarks? No, let's thank you for this interesting talk.